This is part 2 of the RL circuits lab. We've modified our circuit setup a little bit. Now instead of having the light bulb connected, we're connected through a 10 ohm resistor. We're still connected to the larger of the two inductors, and now we've connected voltage probes both across the resistor and across the inductor so we can see what's happening to them with time. So if we turn on data collection in Logger Pro and start collecting data, and turn the switch up, and then turn the switch down. Largely, this just behaves like I have two resistors that are in series. When I'm sending current through there, the potential difference is established across each of them. Because this large inductor has a larger resistance than the 10 ohm resistor, it gets a larger potential difference across it. So that's shown by the red line. The blue line is the potential difference across the 10 ohm resistor. So following the directions in the lab, I'm going to go ahead and change the data collection rate to see if we can see the effect that we're after. So rather than taking data for 18 seconds, I'm going to take it for only 1 second, but I'm going to sample it at 2,000 samples per second. And now I'm going to try again and see how coordinated I am on starting the collection and getting both of these effects going. All right, looks like we got what we were after here. So what we notice is that we're going along at the start, and then when we flip the switch, the voltage across the inductor spikes up to a maximum voltage momentarily, and then goes down to a steady state voltage that's the same that we saw on the earlier capture, whereas the voltage across the resistor ramps up, not slowly, pretty quickly until it reaches its steady state voltage. Let's just go ahead and zoom in on that part of what we see. So here's the little spike that we're seeing, and here is the increase in voltage across the resistor. So it asks us to try to explain this using what we know about Faraday's law and Lenz's law, and the way I think of it is this. When I initially try to send a current through this system, that inductor resists against that, and so when the inductor is resisting the current flow, essentially it's stopping current flow in the circuit for a moment. That means if you use Kirchhoff's voltage rule, the voltage across the resistor will be zero because no current will be flowing through it, which means the voltage across the inductor must match the voltage of the battery. But after the inductor loses that fight, once a steady current flow is established in the circuit, then the voltage drop across the inductor is somewhat less, even though it's still a larger voltage drop across that inductor than it is across this resistor. So we should be able to see the same effect if we connect to our other inductor here. So I'm going to turn the circuit off, see that my potentials both go back to zero, hit my data collection, zoom in on that. And again, the red is measuring the voltage across our inductor. We see that spike there. But now the steady state voltage across that inductor is much smaller than the voltage across the resistor, because in this particular situation, this inductor has about half an ohm of resistance, whereas I still have my 10 ohm resistor in my original circuit. I'm going to go ahead and change my experiment to use the triggering function. So instead of collecting for 1 second, I'm only going to collect for 1/10 of a second. I'm going to try to collect 5,000 samples a second, and then I'm going to set this to trigger when the voltage read across the inductor goes above 1 volt. I'm going to switch back to my larger inductor. It's going to show this effect a little bit better. All right, so now when we start collection, nothing happens because we haven't triggered. I'm going to turn it down in the downward to get 0 across both of them. Again, that was a dropping potential, so that didn't trigger. And now if we flip this up and zoom in, we can see that the voltage spiked and then went down here, whereas the voltage across the resistor grew with time. Do that one more time. All right, so that's the basic setup of the experiment. What I'm going to do is save logger profiles of 4 different combinations, and you can use those to do the analysis at the last part of this experiment. So right now I've got the large inductor hooked to a 10 ohm resistor. I'm going to produce a logger profile for that. I'm going to also have the large inductor connected to a 51 ohm resistor, and then I'll do the same 10 ohm resistor with my smaller inductor and the 51 ohm resistor with the smaller inductor as well. If you are choosing to write up this lab as a lab report, you only need to pick one of those combinations to develop the models for.